All right, it looks like we're at about 1:30 here, so I'm going to kick it off because this is about a 60-minute presentation. So welcome. Thanks for coming today. My name is Brett-Hollman. I'm a solutions architect. I'm part of the solutions architecture organization. We work with customers such as yourselves, helping you guys understand best practices, best way to migrate apps to the cloud, and so on. So there's many of us around at the conference. You can come by the booth and talk to a lot of different solutions architects in the organization. So today we're going to talk about building highly available applications in Amazon Virtual Private Cloud. So let's get started. So what you're going to learn about today is, first off, we're going to deal with the question is, what is Amazon Virtual Private Cloud? What's the best way to define it? Then we're going to go through some of the common use cases for Virtual Private Cloud. We're going to hit a few of the basics around VPC and some definitions. Then we're going to talk about why you might want to move to VPC. What are some of the advantages that you have inside of VPC over maybe classic EC2? Then next we'll move over to connecting your own data centers with your virtual private cloud and how that might work. Then we're going to kind of shift gears and go into more of a high availability set of what I call design patterns. So we're going to talk about design patterns for making your virtual private cloud highly available. And then we're going to go and transition into building a highly available app inside of your virtual private cloud and some of the design patterns you might use for that. And then lastly, we're going to finish off with a demo of Chaos Monkey, acting against an application I created for this demo purpose. So that'll be our wrap-up. All right, so what is Amazon Virtual Private Cloud? Well, really, it's a private section of the AWS cloud that you actually get control of. You own the virtual networking topology. You define the IP addressing scheme. You really have complete control over defining the footprint for a data center that you want to build virtually on top of Amazon. And so you're defining that data center footprint, so to speak. And most easily put, it is a virtual data center on AWS. That's really what you're building with Amazon Virtual Private Cloud, is a virtual data center on top of Amazon Web Services. And one thing to note here, it's not just a data center, a virtual data center on AWS, but it's actually a highly available data center if you build it correctly. So this virtual data center that you're going to build out can actually be spread across a region. And you can actually build a virtual data center that sits over the top of many physical data centers inside of a region on top of AWS. So there's lots of capabilities that gives you that you wouldn't get in a traditional data center topology. So what are some of the common use cases for VPC? So I already mentioned this, designing a virtual data center on AWS. That's a great way to think of it. Great for many enterprise organizations. They're already running their own data center footprint. Basically, creating a VPC on top of AWS is adding another data center to that footprint. And that's a way to think about it. It is really a virtual data center topology. So first off, you build out your network topology on top of AWS. We're going to talk a lot more in detail about how you do that. But then once you've done that, you actually just add it to your data center footprint by connecting via VPN or Direct Connect, a private layer 2 circuit, to connect your virtual private cloud or your virtual data center on AWS back to your overall data center footprint that you already operate. So once you've done that, now you have the ability to do things like run directory services in AWS, replicate your Active Directory, or run directory services. You can emulate your network configuration that you're running in your own data centers and actually run a similar network configuration with a lot of the virtual networking topology controls you have inside of VPC. You also can take your encryption that you're running inside of your own data center, and you can actually hold those encryption keys inside of a cloud HSM appliance you can deploy inside of your VPC. So you can use the same encryption you're using in your own data center over in your virtual private cloud. Also, when you talk about backup, you might have backup appliances that are running over inside of your own data center. You can actually push those backups to the cloud and take advantage of that storage in S3 or Glacier, where it's really unlimited. You only pay for what you use, and it's unlimited in terms of growth potential. And lastly, you can run on-premise apps. You can run cloud apps. You can run hybrid apps. We're going to talk more about some of that today. So this is the picture of a multi-tier public web app inside a virtual private cloud. And it doesn't look that much different than the classic world, with a few exceptions. If you take a look, I'm running a lot of my servers. I don't know if this laser is going to work. Probably not. But I'm running a lot of my servers in private subnets. You notice my web servers are running in private subnets. The only thing I'm actually exposing publicly is my public load balancer. Further, I'm actually doing a private load balancing tier inside of there as well. I've got a load balancer that's only privately addressable between my web and my app tier. So there's a lot of advantages here. We're going to talk through many, many more as this presentation goes on, but that's a start. Oh, excuse me. You can also create private or hybrid applications inside a virtual private cloud as well. So this would be an example of a private or hybrid app. Here we got the same application running, except we're not connecting to it through an internet gateway. We're connecting to it through a VPN gateway, which is something that exposes either Direct Connect or VPN access into the virtual private cloud. So again, my virtual private cloud is privately addressed if I choose. And now I've got users that can connect from the internal user over on the left, connecting through the VPN gateway and it actually hitting that private web app. Further, I could have that internal user hitting an application that's over in their corporate data center, and maybe there's an analytical workload that's part of that overall architecture. So maybe I'm shipping data out to the cloud and running things like EMR or Redshift or something like that that's doing analytical type work that's part of my overall application infrastructure for this particular app. Also, disaster recovery is another very common use case for using virtual private cloud. And we've got a disaster recovery white paper or a DR white paper. If you go to aws.amazon.com/whitepapers, you'll find a whole list of all our white papers. There's a great disaster recovery white paper. It talks through 4 different scenarios you might use for DR in the cloud. These are, just to list them, backup and restore, pilot light, warm standby, and active-active multi-site solution. And so this is a picture of the disaster recovery scenario for pilot light. And in the pilot light, what's happening is I'm running a stack over in my own data center, as you can see over on the left. And then I've got that stack running. What I'm doing is I'm replicating my database server over to a database server running on EC2. And I can be running a very small database server over there compared to what I'd run in production, because all it needs to be able to do is to be able to receive the replication. So I've got the database server running, and I'm replicating my data over to VPC through my VPN tunnel or through my Direct Connect. Then I've got a web server and an app server that I went and configured to mirror my web server and app server over on my corporate data center. I created an AMI, I launched them, and then I stopped those servers. So now all I'm doing is paying for storage on those servers. So all I'm paying for in VPC is the VPN connection, the database server, and the storage for the web and the app server. So I'm paying very little to have this application mirrored over inside of Amazon Virtual Private Cloud. And so now what happens if I've got a disaster? I would go and I would promote the slave to master. I would probably stop and restart that database instance to move it from small hardware to very large hardware. Maybe I'm moving up to a 4XL high memory instance. And then I'm going to go and start my application in web tier and scale those tiers out. And I literally can do that. I can have a script ready that I kick off and does all of that work, in a matter of a few minutes with boot time. And then I repoint my DNS, and that's called the pilot light. I'm paying for very little in terms of compute in the cloud, but I can stand up my app pretty rapidly. Again, all these different scenarios that I just talked about for DR, there's a different cost for each one. So this is kind of still on the lower end. So let's talk about a few basics for VPC and do a few definitions as well. All right, so first off, VPC stands for Virtual Private Cloud, and when you create a VPC, you're choosing a CIDR block to start. So, I typically tell people to start with a /16, a large block of IPs that they want to use for their data center footprint on AWS. From there, you can subnet that out, create subnets or other networks inside of that larger CIDR block. And then from there, you can actually deploy ACLs or network access control lists around that particular subnet block, which specify the ingress policies and egress policies allowed for that particular subnet. So I can implement security at the security group layer, like people commonly know of with EC2, but I can also implement security at the network layer as well. And I can do it in independent subnets. Then I can create route tables, and a route table specifies how a particular subnet is allowed to route, what gateways can it egress, and so on. From there, I can create a VPN connection to tie it back to my own corporate data center footprint. That usually is a pair of redundant encrypted connections. I can also use Direct Connect rather than VPN connections. And Direct Connect is going to be a private layer 2 circuit or a cross connect, if you're co-load at one of our Direct Connect locations, that get you privately a private Ethernet connection between your router and the Amazon router that you're facing. So now, let's say somebody needs access to your VPC. There's a couple things that they need. They either need to come in through the VPN or they need to come in through the internet. So we're going to define a couple concepts around that. First off, the internet gateway. This is what provides a particular subnet access to the internet from inside of your virtual private cloud. So once you've created an internet gateway and attached it to your virtual private cloud, you then can define a route out to the internet for a particular subnet. Virtual private gateway is very similar. It's the same thing, but for that VPN connection back. And this particular subnet talk to my corporate data centers or my LAN environment back at headquarters. The customer gateway is going to be your router or firewall that faces AWS over the Direct Connect or VPN connection. We're going to dive deeper on NAT today, Network Address Translation, which is a service that you run inside of VPC, and it provides port address translation for servers that are sitting in private subnets that don't have internet access to get out to the internet to download software patches, call APIs, and so on. Security groups, those are things that are common to EC2. If you're an EC2 user today, you know what these are. And this is really the firewall that wraps your EC2 instance, and it specifies inbound and outbound access policies for that particular EC2 instance. And lastly, availability zones. An AZ is either a data center or a cluster of data centers that are on a particular piece of land, and every region has multiple availability zones. They're built to be fault tolerant from each other. They're typically separated by geography, and they're built to be fault tolerant from the other availability zones in the region. Okay, so what are some of the features of VPC? And I've already mentioned a few of these, so we'll cruise through these pretty quick. But you control the IP addressing you're going to choose for your virtual private cloud. You've got the ability to subnet that further. From there, you can deploy ACLs with the egress and ingress policies. You can assign multiple IP addresses inside of VPC as well to your EC2 instances. And you can also assign multiple elastic network interfaces. We're going to talk more about that later and where that becomes useful. You can also run private load balancing services, as I showed you in a slide earlier. And then lastly, you can bridge your VPC with your on-site infrastructure. So again, it just becomes another data center in your data center footprint. Just another set of IP address ranges you can go and launch services into. It's easy to scale up and launch into VPC. Don't have to order anything. You just call the APIs. So here's a picture of some of the security controls inside of VPC. So for this particular example, let's say we got the 10.0/16 network. So first we picked that particular network, and then we went and decided to subnet it out into a couple subnets, the 10.0.0/24 and the 10.0.10/24. Then further, I'm going to go wrap ACLs around that subnet if I choose to define what that subnet is allowed to do in terms of ingress and egress. And then from there, I define route tables, which specify how a subnet can route out. Can it route out through the VPN gateway? Can it route out through the internet gateway? Can it route out through both? What IP ranges route where? That's the type of thing that happens in the route table. So lastly, I would go and deploy an instance. When I deploy an instance, I choose a security group that I'm going to launch it into. Here I get the ability to define inbound and outbound access policies around my security groups, whereas in classic EC2, I can only define inbound policies. And then I can actually specify an exact IP address inside of a subnet. And then further, if I go and stop and restart that instance, it's going to retain that same IP address scheme that's on that particular instance right there. So if I stop the 10.0.0.6 and then I restart it, it's going to have the same IP address. It's a little different from the classic EC2 world. So here's a little example that I like to walk people through. This would be your network on the upper right, the 172.16/8, the internet on the left, and then we've got our virtual private cloud down below. And if you take a look at this particular case, we've got what we're calling a public subnet over on the bottom left, and a private subnet on the right. And what makes the bottom left subnet a private or a public subnet, if you take a look at all the servers there, we've got a bunch of web servers and a NAT server. If you take a look at them, they're all privately addressed for that subnet, and they also have public IPs assigned as well. And then if you look at the route table, you'll notice there's a couple routes. There's a local route, the 10.0.0.0/16. Every route table has a route that's local that says that everything in the VPC can talk to each other, barring any ACLs or security groups that prevent that. We'll talk a little bit more about that later. And then there's a default route out to the internet gateway. This means that any route that hasn't been further defined, that's more granular, is going to actually go out to the internet to terminate that traffic. So these servers all have access to talk to the internet and receive requests from the internet as well. If you look at the subnet on the right, it's called a private subnet. It's labeled a private subnet. And the reason why, again, it's got a local route, but now it has this route out to the VPN gateway for the 172.16 network. And then lastly, there's a NAT instance, a route to the NAT instance, and that's where our default route is pointing in this case. And what that means is that when these servers want to, let's say, call a public API or put something in S3 or get something out of S3 or download a patch or download software, they can actually go out and make a call to the NAT instance. The NAT instance will port address translate that request, allow them access out to that internet destination, and then allow a stateful response back, similar to your laptop behind a firewall when you're sitting at your own corporate headquarters. You don't have a public IP assigned, but you can still get out to the internet. Same idea here. Okay, so some considerations around building out your virtual private cloud. So first off, I say, typically you're going to want to choose your CIDR block that you pick for your VPC wisely. You're going to want to pick something that doesn't collide with your overall corporate LAN environment or your data center footprint. So pick a unique IP address range that you haven't used somewhere else already, unless, of course, you're building this for a DR scenario where it's a standby site. So that might be an exception, but typically you want to pick something that doesn't collide with your overall corporate LAN environment, your data center footprint. You also want to pick something that's big enough for future growth. So you can run multiple VPCs, and that's very common as well. But if you're building out a VPC and you're going to have a lot of shared resources in there and you want to grow and grow and grow this, start with a /16. It's a great place to start, and then you can subnet that out further. Now, when it comes to subnetting, there's kind of two different ways to think about this. There's the keep it simple method or the divide by function. And those are my terms, so they're not something you're going to find in our documents. But keep it simple. I'm going to go in, and for each availability zone I want to run my VPC on, I'm going to define a public and a private subnet, a large public and a large private subnet. Pretty simple. If I'm running in 2 AZs, I've got 4 subnets, right? That works well if you want to just run a simple VPC. But let's say you want to, let's talk about the divide by function here. So that might be dividing things by tier. I might have a database subnet for each availability zone. And maybe I've got an app subnet. Maybe I've got some analytical workloads that I've got running in another subnet. Maybe I've got a couple different web tiers. Maybe I want to put those in different subnets as well in each availability zone. So I'm dividing by function. And that's where network ACLs versus security groups comes in. So the way I like to explain this to people, at least there's many philosophies. There's no right answer. But a good answer is network ACLs are great for like a network security organization, right? Somebody comes in and defines the data center footprint, designs how we're going to lay out our subnets. They divide up by function, and then either day one or later, they can come in and deploy ACLs around those particular subnets, specifying what's a coarse-grained set of rules around what the universe is that's allowed to talk into this subnet and out of this subnet. So they might say, hey, this database subnet, we don't want anybody talking to it except these couple IP address ranges, and we're only allowing these ports open, right? And then further, some application team is going to come in and launch a database or launch a web server, and they might say, hey, I'm going to put a security group in place, and I'm going to open it up to the whole world, right? Well, okay, the network security organization already put a set of controls and rules around a particular subnet about what traffic's allowed in and out. So the ACLs, the security groups now have got to live inside of that set of rules. You can open up more ports, but they're not going to be exposed because you've locked them down at the network layer. So I typically think of ACLs as something the network security org takes care of, and security groups being something that the app team takes care of when they're launching instances. So the security groups, or the ACLs may have been open to many ports, but the security groups might say, the app owner might say, well, I only need these 3 ports open. That's kind of the way I make sense of it. So why move to VPC? Well, first off, hopefully you won't be sleeping on your data center floor if that's the case. A couple other reasons. First off, it's an expandable data center. It's something you can burst into very rapidly. You can deploy resources in very rapidly. It costs you $0 to run a VPC inside of AWS. You only pay for the resources you launch into VPC or your VPN connection or your Direct Connect. And literally, to turn up a VPC and have it ready for the day that you're ready to actually start using it, it costs $1.20 a day. It's 5 cents an hour to run a redundant pair of tunnels into AWS. So for $1.20 a day, you've got a data center on your footprint that you can quickly deploy services to, dev and test environments, and so on, as that need becomes, as projects require it. So another reason, all new accounts today already default to VPC. So many products like EC2 and so on, we'll talk more about exactly how this works, but the idea is there's already such a concept as default VPC if you're opening up new accounts anywhere except US East. And really what that is, there's a lot of features we've exposed inside of virtual private cloud, and what we've done is create this concept of a special VPC. When you create a new account, we create a VPC for you, and we create a public subnet inside of that VPC, and then any untargeted launches of EC2, RDS, elastic load balancing, EMR, and so on, any untargeted launches where you're not specifying a specific VPC to target those to, they're going to go to your default VPC, which really acts a lot like the classic EC2 world. You get a public IP, a private IP, a public host name, a private host name. You get all of those things, just like the classic world, but you're inside of a virtual private cloud. You can take advantage of all these other things we're going to talk about inside of there. And so each region has one default VPC, and each AZ has one default subnet. So if you're signing up for new accounts in regions other than US East, you're defaulting into VPC automatically. And again, as you're launching resources into these default VPCs, you can take advantage. You can further subnet it. You can add private load balancers, private subnets, and so on. So what are some of the functionalities that are provided by VPC or moving from EC2 to VPC? And static private IP addresses, being able to allocate those to your instances. The ability to allocate multiple IPs and multiple elastic network interfaces. Dynamic security group membership allocation and configuration. You can go and change the security groups after you've launched the instance. You also can do outbound packet filtering on your security groups. You can deploy network ACLs and, again, private load balancing. So, okay, so let's shift gears into how to connect VPC with your data centers. So, first off, there are two options, VPN connections or Direct Connect. And for a VPN connection, you can do redundant IPsec tunnels. That's what's recommended. This also supports BGP or static routing, so you can say, hey, here are the routes from my particular data center that I want the VPC to know about over the VPN connection, or you can say I'm going to exchange routes over BGP. You can also run redundant customer gateways to build in some redundancy on the LAN side. So a single VPN connection communicates with multiple data centers in multiple availability zones. So you got this virtual data center. It's running in multiple AZs. And one VPN connection can talk to both the availability zones in this particular diagram, or all three if there were three. You can also do multiple VPN connections. So all your offices can talk to a VPC through the virtual private gateway. We also have something called Cloud Hub, where all these offices could talk to each other. And the Cloud Hub, the virtual private gateway hubs the traffic between the offices so that they can communicate with each other. Almost like, think of it as a cloud hub in the middle. I guess that's the term of the product. But redundant tunnels for your VPN connection. So when you set up a VPN connection, you're going to want to put together multiple tunnels, and those are going to terminate on different hardware on the Amazon side. So again, if there's maintenance done on one, traffic will flow over the other. You also can run redundant customer gateways so that you're building redundancy into it on your side of the equation. So it's not just dual routers on the AWS side, but you also got dual routers on your side. So you're going to build redundancy into your LAN environment, with something like HSRP or VRRP. So what is Direct Connect? We're going to go more into this in the next couple slides, but really it's an alternative to using the internet. You're going to use a third-party provider, telecom provider, or a colo provider. It's a private network connection. You're going to be able to reduce costs and change your network characteristics in terms of having a more consistent connection that you're communicating to AWS with. So you might say reduce bandwidth cost of bandwidth. Well, I'm going to have to come with a private circuit, and that's going to cost me some money every month to come with a private circuit to AWS. But there's a delta between the cost for data out over Direct Connect versus the cost for data out over the internet. If you come with your own pipe and the data is being transported by you out, you pay a certain amount of cents per gig out, right? And if you're using our internet pipe to get data out, it's going to cost more. So let's say the delta's 8 or 9 cents a gig, and I might be off on that. I'm just using some numbers. But eventually, you're going to make up that. If you're pushing enough data out, if you're running big data, if you're running analytical workloads, you're pulling a lot of data out of AWS. At some point, there's going to be a break even where you're actually saving money by using Direct Connect and getting better network performance. So again, more consistent network performance. You're going to be buying a dedicated circuit from a carrier, potentially a wavelength, a gigabit wavelength, or a 10 gig wavelength, or a 10 gig or a gig private line, or potentially a layer 2 packet over Ethernet type solution, or something like that. But these things typically have much better performance than the internet. You should be able to get a pretty well-defined latency from your carrier. You can also connect privately to your Direct Connect with Direct Connect as well. And we're going to talk more about that. We do have many Direct Connect locations. There are currently 11 locations. You can find out more details on our website. We also have a variety of partners for Direct Connect. So there are colo partners such as Equinix and CoreSite in the US, and we also have telecom partners, a variety of partners that can deliver circuits from your data center over to AWS to the Direct Connect regions and get you that cross connect over to the AWS panel that faces our router. So let's look at a few Direct Connect architectures quickly. So first off, this would be a basic Direct Connect with no redundancy built in. We've got our router. We got the Direct Connect connection. It's terminating on the AWS router inside of the cage. You go turn up a port from the console. Say I want a gig port, you're going to get LOA CFA back from us, a letter of authorization, and a carrier facility assignment of where you cross-connect to AWS. You give that to your carrier, and your carrier will go and order the cross-connect from the Direct Connect colo provider to get you over to AWS on that particular panel, on that particular port. And then you go through the activation process, turn up your virtual interfaces, and so on. Now, as you see here, you can have multiple virtual interfaces over a Direct Connect, or sub-interfaces. And these are VLANs. So you can have a public VLAN that faces AWS, where people in your data center or on your corporate footprint talk to AWS public services, and this would be preferred over the public internet path. So people can go put things in S3 and get things out of S3. Let's say you've got workloads that are pushing a lot of data into S3 for big data, for analytical workloads or big data workloads, and you're generating a lot of data over your data center. You want to push it to AWS, and your internet connection maybe isn't enough, maybe you can't get enough throughput. You might use a public interface over Direct Connect to do something like that. Hybrid apps would be another case. And then you can always create virtual interfaces that are private over to your different VPCs, as is done here. There are two different VLANs, VLAN X and VLAN Y, I believe, inside of the diagram, that actually connect your corporate headquarters to two different virtual data centers running in a region. And you can actually relegate virtual interfaces to sub-accounts as well, or other accounts. This would be a little more of a robust solution for Direct Connect here, and this is probably the more recommended solution, where you've got dual routers on, or a single or dual routers on your end, facing dual routers on our side. And you can do this, and if you order 2 Direct Connects, you can have link level redundancy and router level redundancy on our side. You can also run dual Direct Connect like locations, so you're actually hitting AWS in a single region at 2 different buildings. So in US West 1, Northern California, you can meet us at 1 Wilshire, Core Site 1 Wilshire, or Equinix San Jose. If you're on the East Coast and you're trying to hit US East, you can meet us at Equinix Virginia or Core Site New York. And so now you've got building redundancy or location redundancy built into your solution. Okay, so now we've talked a lot about what are all these things. We're actually going to shift gears into making this highly available. So we're going to shift into more of a design pattern type environment here. So in this case, I've got a problem statement where I've got an application that runs either 1 on a single instance or 2, and maybe it only runs on a single instance. This application doesn't horizontally scale, so it's a single point of failure in my architecture. Maybe I want to run a hot standby alongside it. Or this could also just be used for upgrades as well. But I've got the ability to define an interface called an elastic network interface. When I launch an instance, it's always going to have an Ethernet 0, and that's not movable between instances. But if I go and attach an Ethernet 1 interface or an Ethernet 2 interface and create an elastic network interface and attach it to my EC2 instance, I can actually move that within the subnet to another instance. So let's say I do have a hot standby and I want to move the interface. I don't want to change it. People are pointing to IP addresses and whatever. I don't want anything to change underneath the covers. So all I need to do is move that ENI from one instance to another, and I've got the ability to do that with this floating interface pattern. So, I mean, some of the pros here, I don't have to update DNS. Fallback is as easy as moving back my ENI if I'm doing an upgrade or something like that. And anybody that's pointing to public or private IPs on that interface, they all go with it. So everything goes with that interface. So it's a virtual elastic network interface. And the last note is this is only good within a subnet. So you can only move them within a subnet, and a subnet is confined to an availability zone. So you can't move these between availability zones. So we talked a little bit about on-demand NAT. And here the problem is I've got these things I want to remain private, but I want them to be able to talk to the internet, to download patches, to download software, to call APIs, to put things in S3 and get things out of S3, to call DynamoDB, all of those services that would be public. I might have those needs inside of my virtual private cloud. How do I expose that to things that are running in private subnets? And deploying a NAT on an EC2 server is the way you do that. You deploy a NAT, you take your subnet, and you create a route that points the default route or a specific set of IP ranges to that particular NAT. And then when any requests go out in that IP block, they'll go through the NAT, and the NAT will do a port address translation to give, again, a stateful request and response to that internet destination for your request. So this is a very common pattern. But next you say, well, OK, I deployed NAT, but it's a single point of failure now. Let's say my application depends upon NAT. What do I do in that case? So then I'd say, what you really want to think about is high availability NAT. How do I build a NAT that's more highly available? So In this case, I'm going to run NAT in independent autoscale groups in each availability zone. And so these autoscale groups have a min of 1 and a max of 1. And let's say that NAT dies. What's going to happen? Autoscaling is not meaning to scale things out now. All it's doing with a min of 1 and a max of 1 is make sure that one instance is healthy. If that instance dies or degrades, it's going to kick it out and launch another one. And so autoscale will take care of launching the new NAT. But then how do I set up the NAT services again here? Well, what I do here is, as part of my launch configuration, I'm going to assign a public IP. I've got that capability now. That's something we made available shortly in the last 4 to 8 weeks, I'm going to say. And then lastly, you can kick off through user data a script that would actually go and update the VPC route table for that particular subnet to point to the new NAT. So the NAT's actually bootstrapping itself. It's actually saying, hey, I'm the NAT. I launched with a NAT AMI, and I assigned an IP address, and now I've got public access, so I'm going to go make the API call out to go and update all the routes that are supposed to point to me. So the pros here, I mean, your NAT application is much more HA than it was before, where there was manual intervention that was required to stand up a new NAT. But, you know, and you've got limited downtime, but I mean, it's going to be a few minutes of downtime if it goes down, right? You've got to, you know, auto-scaling needs to discover it. That takes a little bit of time, and then you know, once it launches it, it's going to take a little bit of time to boot as well. So you know, can I accept that? Well, we've got another pattern called squid proxy. So I liked the pattern before for its simplicity. It's a really good pattern. There's an article one of the ProServe guys in Irvine in my office wrote on squid proxy. You can go find it if you do search for AWS squid proxy. I think it'll be the first link on Google. And and it has all the CloudFormation templates as well, so for setting this up. But here the problem is, again, standard NAT. I don't want to be dependent upon one instance. Maybe I can't take the amount of downtime of a few minutes while that NAT reboots. Maybe my application is dependent upon it. And lastly, maybe I need to push a lot of data out to S3, do a lot of puts and gets out to S3. And maybe my throughput is going to be way beyond what a single NAT instance. I might have hundreds of instances that are trying to put and get things out of S3. And you know, one single instance being the network bottleneck is probably not the right way to operate on this. So what do I do here? I run a squid proxy configuration in an autoscale group. I might have that autoscale group scale on network I/O or something like that. And then I put a proxy layer in front of it, a private load balancer. And then when I boot these EC2 instances, I have them bootstrapped to proxy all their connections for HTTP and HTTPS out through that particular private load balancer. So now if a squid proxy fails, what happens? I've got as many more as I had. I might have a min of 4 in that tier and a max of 20, let's say. And so I've got 3 others that are sitting there, and autoscaling is going to launch that 4th one again. Further, as network I/O goes up, it's going to scale up that squid proxy layer, and it's going to scale it back down as network I/O goes down. So really good pattern here for HA NAT. But you know, there are a few cons. More maintenance, more cost, all of those things, right? So you know, you got to balance the pattern you use with the cost and the administration that goes along with it. Okay, so we're going to shift gears now to application design patterns and talk about some different patterns for making your application highly available. And you know, the Amazon CTO Werner Vogels says quite often, everything fails. So you really got to build your application with that mindset of everything fails. So you know, you really need to design your application to meet your SLA and your price point. So at some point, those two are going to intersect. There's the amount that it costs for your application to be down, the RPO and the RTO, and you need to balance those against the cost of what it takes to run a highly available application and figure out where that crosses. So just a couple metrics here. For a 5.9 application, you're talking about 5 minutes of downtime a year. For a 6.9 application, you're talking about 30 seconds. So how do you design your application and balance it with expense for your particular scenario? So we're going to start off with the multi-data center pattern. Now, this is probably a pretty elementary pattern for most people that have been using AWS for a while. You run a load balancer. You run multiple servers behind that load balancer in multiple availability zones. That load balancer health checks the instances. If an instance fails, that load balancer is going to kick that instance out of the load balancing cycle, and it's going to load balance to the other instances. And if that instance becomes healthy again and starts passing health checks, it'll start serving traffic to it again. So now I'm more highly available. I've got multiple servers running in multiple availability zones, and I'm load balancing traffic, and I'm health checking them. Further, I can actually use autoscaling and wrap autoscaling around those EC2 instances to kick out the bad instances, rejuvenate them, scale up, scale down, and it will actually register instances with the elastic load balancer, and it'll also deregister instances and shut them down. So there's a couple things that are key here. So let's say I'm going to use this multi-server pattern. First off, when I've got somebody uploading content to my site, let's say I've got user-generated content. Where am I going to put that? Am I going to store that avatar or that video or photo on that particular server? Probably not, right? I'm going to need to have that. I might have 20 servers in my web fleet, and they're not, the other 19 aren't going to know about it. So I want to think about how I manage that type of interaction. Do I put stuff in S3 cloud storage, or do I put things in an NFS behind? How do I manage that? And we'll talk about that next. Also, if I'm going to be scaling up and scaling down, am I storing session state on my servers? So am I storing session state in cookies? Am I storing it back in a backend database or in a key value store? Or am I storing it on my server? So I've got user session information, so I need to direct users to the same server every time. Now, as my servers get bogged down and I scale out, I can't push any of the traffic out to those other servers. Maybe new users can go to new servers, but the current users that are bogging down a server can't be moved out there. I'm not stateless. I'm very stateful. People need to go, and session affinity needs to be applied, or I need to direct a user to a particular server using session stickiness, which you can do with our elastic load balancing service, but there are better patterns. So we're going to talk more about that as well. And hence the web storage pattern. So this is really the pattern of using something like S3. Here the thing is, one, I've got content that's going to be replicated. Maybe it's user-generated content. I need to put it somewhere that's common to serve it out of. Or two, maybe I just want to take load off my web servers. I mean, that's a very, why should I serve JPEGs, videos, CSS, JavaScript? Why should I store all those big files on every web server and serve it off the web server? Why not serve it from a common repository such as S3? Taking load off my server is also a key pattern here. So the solution here is to actually store your static assets in S3. And S3 is a cloud storage solution, web storage solution, and it's actually capable of serving that content up. So storing all those heavy static assets in something that, other than your web servers, that can actually serve that content is actually a great pattern here. And so S3 is going to eliminate the need to worry about that load on your servers. You can actually put more traffic on your actual web or app tiers rather than actually serving static content. You're not going to max out your network as easily. S3 is highly durable. You're talking about 11 nines of durability in terms of the storage, the objects you place in S3. So when you place an object in S3, it's replicated around the region many times in at least 3 different data centers. So you're talking about 11 nines of durability on the objects you store there. So very durable. Lastly, you can actually use S3 as the origin for your content, for our content delivery network or other content delivery networks as well. So CloudFront is our CDN, and CloudFront or S3 can be the origin for our content delivery network. And what happens when you put the content delivery network in front of it is you're putting a global caching network in front of these static assets so that the assets get moved closer to the user. So it allows your web pages to download faster, to load faster, to serve that video or that heavy image or whatever it might be faster and just render your page quicker overall. So lastly, you might say, I've got a lot of content. I need to get it up on AWS. I've got terabytes and terabytes of content. It's going to take me forever. Got all these videos. Yes, you can technically ship those videos to us in a box using AWS import-export. So state sharing. So we talked a little bit about the idea of storing state on a server and not being able to scale out horizontally. So if I want to scale out horizontally, and I'm storing all session state on a server, well, now when that server gets filled with users that all have their session state stored on it, when I open up the next server, what's going to happen? I'm not going to have any users on it at day 1 or at minute 1. And then over time, my new users might end up on the new server. But so in this state sharing model, I want to move that state sharing off into a key value store or a database or something like that. So commonly, there are plugins to move state directly for PHP and I think a few other languages. There's a plugin to move it directly out to DynamoDB. That's a common place. Also using Elasticache Redis or Memcached is another common place. Putting it in MySQL. The one thing you want to make sure is you don't make that a bottleneck now. So if you're going to put all this stuff in Dynamo, make sure that your Dynamo reads are high enough that you're going to be able to handle all those session reads you're doing out of Dynamo. Same with your using Elasticache. Make sure you got enough cluster nodes as well. this actually alleviates the problem now. I don't have to worry about session being tied to a particular server. I'm stateless. So now I can scale up, and every user request, doesn't matter who it's from, can go to any of the servers in the fleet. And then as I want to scale down, I can scale down as well without losing sessions. So good pattern. Highly available database pattern. Here, I want to have a highly available database solution where if I lose my master node in an outage, my application survives. So, the solution to this problem is, and there are many different ways to do this. You can do this on EC2 and roll your own solution. But, we make this very easily doable for you with our RDS solution with MySQL or Oracle. So if you take a look, you can run a master database in one availability zone, run a slave in a second availability zone, and have synchronous replication between the master and the slave. You can also run read replicas with MySQL and take all of the reads for your application and push them against the read replicas, or any offline reporting and have it run against the read replicas, and then only your writes go against the master, so that, hence improving your I/O that you have for your particular application in your database solution. So the pros here, you get one connection string, one to the master. If the master goes down, we're going to change that connection string over to the slave, promote the slave to master, spin up a new slave. So it takes about 2 to 4 minutes for that to happen. We recommend implementing retry logic on your database requests. If you make a request and there's no response to that connection, back off and make another request. And that's the recommended approach. But in a short amount of time, you'll fail over from master to slave. So this makes this a much more highly available database pattern than a standard running on a single instance. Bootstrapping an instance. So in this case, I've got code releases that happen often. And I don't want to create an AMI every time to put into my auto-scale group. Let's say I'm releasing a couple times a day. That's a lot of work. And then maybe I'm copying those AMIs off to another region. So it's a lot to keep track of and a lot of work. So the solution here is to develop a base AMI and then bootstrap the instance during boot to install software, get updates, install source code, and download your source code off of GitHub or wherever it might be, S3. The pros here, you don't have to update your AMI very often. And you can live with an AMI, that you only update every once in a while when you got to install a new package or new dependency, or update your OS with some security changes or whatever it might be. The cons here are that bootstrapping in its entirety takes longer than booting from a golden AMI. So if you think about the golden AMI, that's where all the bits and bytes to run your particular server are sitting on that particular disk image. And when you boot, it boots really quick. When you start with a base AMI and then you bootstrap, it takes a little longer because I'm going to be installing those things, libmagic, whatever it might be, right? All the different packages and pulling my source code off and running those processes during the boot process. So there's a balance here. Do I need to boot fast, or do I want to have ultimate flexibility? Well, maybe I meet somewhere in the middle. Maybe I've got a lot of the packages already installed. I've created a custom AMI. All I'm doing is installing source code or maybe a few things during the boot process. So I'm meeting somewhere in the middle. I'm bootstrapping, but I'm also using a custom AMI that's going to allow me to boot a little faster. So here's an example of bootstrapping. And this is a CloudFormation template I built a while back. And I'm just going to step over here and see if my laser works. Sorry to those of you that can't see the screen. But so here I'm using CloudFormation init to bootstrap an instance. And what I've got basically here is an autoscale group that I created. And every time you launch an instance in an autoscale group, you're launching it based on your autoscale launch config. The launch config defines what the server is going to look like every time you launch a new server with autoscaling. It's going to specify, here's my AMI, here's this, here's that. So in this particular case here, I'm using CloudFormation init to bootstrap. I'm installing packages. I'm using Yum, the installer for my Amazon Linux, to install Apache and PHP. Then I'm using the sources command here to pull all my source code off of a zip file in S3 and unpack it into var HTML. And then lastly, my services command here is it's enabling Apache and ensuring it's running. When it's done all those steps, my server should be running, should be attaching to the load balancer, and I bootstrap my instance. So this instance is starting from a base Amazon Linux AMI. All it's doing here is doing a hello world. I mean, pretty basic, but nevertheless, you get the idea. That could be a very complex application in that zip file that I'm deploying with this particular bootstrap instance example. Okay, so you might say, this is all great. What happens, though, if my application still degrades? Let's say it's a database issue. Let's say it's an application issue. Let's say it's an infrastructure issue. Like we talked about, everything fails. So applications can degrade. Or what happens if I just want to do maintenance? I might just need to do maintenance at some point in time. How do I meet my SLA of 5 minutes of downtime or whatever I set that SLA to per year? And operate to that, with these possible factors that could impact my app. So one of the answers that I like to give people is run a static website in S3. So I might have my web app out there that's a dynamic app, right? It's written in a Java or PHP or Ruby, and it has lots of features and functionality. But I could have a very nice page, index page, product pages, contact pages, anything else that's applicable to my particular application, but it's static. PDFs, all of that. It could be. You can actually create a website in an S3 bucket and actually have S3 become the web server for that static website. And then you can use Route 53 with DNS failover to fail over traffic to that static website when the dynamic website goes down. So this is a great pattern. If you take a look, this is building out a static website on S3. And you define your bucket. You put all your static files inside of that bucket. You can define your index document, your error document, and so on. And then we're going to go create a DNS failover policy, which here I've got a CNAME record of www that's going to point to my Elastic Load Balancer. It's got a routing policy of failover routing, and it's got a record type of primary. So what Route 53 is going to do is it's going to always health check. It's going to health check the load balancer, and as long as it gets responses, it's going to serve traffic to that load balancer. But if that health check fails, well, I've got a secondary policy in my failover routing that points to my S3 static website, which, if I want to be really, if I really want to worry about fault tolerance and redundancy, I might put that in a different region. So now this is going to live, Route 53 is going to fail everything over to that static website in the case here. So, and that's exactly what happens in the example here. Our health check failed. We switched over to the secondary route, and now we are actually serving a static version of our website or our web app out of S3. So what might a highly available application like this look like inside a virtual private cloud with a lot of the best practices we learned? So here we've got our application. There's a lot going on here, but we separated all our subnets out by function. So if we choose to add ACLs later, we can. We also have deployed all of our servers in private subnets. So I'm not putting these servers and exposing them to the public. They might be web servers, but the only thing that needs to be public is my load balancer in this case. We also are using Elastic Load Balancers in front of the web tier and between the web and the app tier. And these are highly available fault-tolerant services as well that heal themselves in case of issues. And so we've got a fault tolerance built in there. We also deployed HA NAT using the auto-scale design pattern we talked about earlier today. We're also using the multi-server pattern with multi-AZ at both the web and the app tier. We're using the web storage pattern. So we're serving all of our content out of CloudFront with S3 being the origin. So we're taking load off the servers. We also are taking all session state and putting it in DynamoDB. We're also using the high availability database pattern. So we've got master and slave with reads coming out of our read replicas in the local availability zone. We're using Route 53 for DNS failover, running a static website in an S3 bucket. And then lastly, we're using dual customer gateways for internal app users that are coming through VPN or administrators or whoever it might be. We're using dual VPN connections, dual customer gateways, potentially dual direct connects. Okay, so this is all great. As we talked about, everything fails. So it's important to test our application out. And there's a variety of load and fault-tolerant testing tools out there. This is an image of bees with machine guns. You can spin this up via CloudFormation. Really, you're spinning up a set of bees, being the EC2 instances, and the machine guns are the requests they make out to your web app to put load on it. I like that little image. So a variety of test tools, Apache Bench, bees with machine guns, load runner. And then we get to Chaos Monkey, which is more of a fault testing tool. And that's where we're going to transition to next. So what is Chaos Monkey? It's really something that targets and terminates instances in a region. Why would you run this? Well, like we talked about, everything fails. So why not test to see what that failure looks like? Know how your application is going to behave in case of an outage or in case servers die in a particular tier. So it's best to be prepared by testing. There are multiple implementations of this. You can do a .NET CLI app, which is what I'm going to demo today. There's also an open source Java services implementation you can use. So what it does is it targets instances in autoscale groups. At least that's what you typically want to be doing. You want to deploy your application correctly so they self-heal at each layer. And so you target autoscale groups to have Chaos Monkey knock these things out and see what happens, how your application responds. So there's an opt-in or opt-out model. We're going to use the opt-in model. I'll show you how it's going to work. It's tunable, so you can set it to how many instances you want to terminate. Netflix runs this during the week. I don't know if this is still accurate, but they used to run it from 9 to 3, Monday through Thursday. So it's almost like a shift. So for our demo, we're going to actually demo. I built an application out that looks similar to the application we looked at a couple slides ago. It's called chaosdemo.holman.me. This is the actual CLI command I'm going to issue against Chaos Monkey. So we're going to log everything to chaoslog.txt. We're going to run this against the US West 2 region. There's my access key and secret key. Anything that's tagged with chaos and a value of 1 is going to be targeted. And then I'm going to kill 4 servers, and I'm going to do it every 15 seconds. That's the duration. So next, we're going to transition into our demo. So give me 1 second here. Hopefully, everything should be up. OK, so here's the command. And we're going to run this. I'm running this on a Windows server here. And right here, I've got the Chaos demo application. And if I refresh this, essentially what the application is, this is, it's fairly crude. No UI. Just a PHP app with no HTML formatting it. But essentially, it's going to tell you the web server you hit with the request, the app server you hit with the request, the web servers in your web tier, the app servers in your app tier, and any scaling activities that have happened recently. Now, these are all from demo runs. And if I scroll through them, you'll notice that down at the bottom, I can actually see when all my servers were launched when I created this demo on October 22nd. But So essentially, we're going to run Chaos Monkey against this and see what happens. I'll just show you right now. Here are my app and web tier servers inside of EC2. They're all running. So those are all the servers. And lastly, we will kick off Chaos Monkey to run against this. So I'm going to kick it off. It says I need to press D to indemnify. So it's running now. It's actually chosen an instance to kill, I0D286B39. And it's waiting 20 seconds to kill the next instance. Okay? So let's go over to our console and refresh and see what's happening there. Okay, so we see an instance shutting down in my web tier, right? If I refresh here, I should see, okay, now I've actually got only 4 instances in my web tier. I've got 6 instances still running in my application tier. So if we go back to here, we can see we've actually terminated 2 instances already. It's killed a second instance. It's waiting 20 milliseconds to kill a third. So there it found a third instance now, and it's waiting the 20 seconds again. If I go back to the EC2 console, I should see now a few instances that have been shut down. OK, so I've got 2 that are shutting down and 1 that's terminated, right? And my application should still be surviving this. I can see now I'm down to 5 application servers and 4 instances in the web tier, right? But my application is still resilient. OK, so now I've got a pending server in the web tier. So I've replaced one of those web servers that died in the web tier via auto-scaling. So I'm launching a new server. I'm down to 4 in the app tier now. So I'm assuming Chaos Monkey is finished now. So it's killed 4 instances. It's done. The process is over. I could have set this to run every 20 minutes, once a day, however long I wanted to run it. And then you can also use the Java services implementation, and I think that's very tunable as well. But as we can see here, if I refresh the console, I've killed a couple instances, and I should have instances that are spawning. This instance is initializing right now, so this is a new instance. It doesn't even have a label yet. And again, my application is still surviving. And so now I've got 5 running in my web tier, 5 in my app tier, and my app tier has got 4 live servers and 1 that's pending that's being booted. So essentially, in a couple minutes, this whole application is going to have rebuilt itself and is going to be back to square one, where I was running 6 web servers, 6 app servers. I've got my elastic load balancers between the tiers and so on. All right, so let's go back to our slides. So there's a variety of other sessions on VPC and Direct Connect at reInvent that I'd recommend you attending. On Thursday, there's going to be From One to Many Evolving VPC Design Patterns. It's going to talk through some of the patterns we talked about today and dive deep on a lot of other patterns as well, and a lot of other good architectural practices for VPC, using multiple VPCs, all the different things you might want to think about. Then there's also another discussion on hybrid cloud architectures with Direct Connect on Friday. Further tonight, there's a pub crawl, so join the AWS startup team to go to the pub crawl. It's meeting over at Canaletto on the Venetian second floor. It's from 5:30 to 7:30. And then lastly, if you're in the startup community, there's going to be a bunch of sessions with Werner Vogels, our CTO of Amazon. And there'll be some fireside chats tomorrow from 1:30 to 2:30 and from 3 to 4. And some startup launches tomorrow at 4:15. So I want to thank you guys for coming. I appreciate you joining the session. Please give your feedback. That's how I know how to get better at this. And if you want to actually ask questions, I'm going to have a number of essays that come up to the front, so feel free to come up and come to us with questions, or I will be in the Amazon booth in the deployment and management area tomorrow from 10:30 to 1:30. Thanks very much.